All right, well, happy Friday. So, you survived PA3, that's good. I will get those graded over the weekend. About a quarter of the class did not have a Git repo that I could access, or it didn't exist. And I sent email this morning about 8:30 through Canvas if I wasn't able to get your repo. So if it's a technical difficulty, right, and you don't know how to fix it, I got office hours right after this class, 11:50 to 12:30. I got office hours at 2 o'clock. Come by and let's figure out how to get your code on the repository. If it's a programming issue, if you didn't make enough progress that you felt you had anything to submit, come and talk to me, right, today if possible, and let's figure out where you are and how to get on track. Okay, I don't want people to give up on this course. I don't want people to give up on this program. PA3 is complex. There's a lot of pieces to it, and it can be overwhelming trying to sort of get all those pieces in working order and get them to play with each other and so on and so forth. But, you know, well, we can work through it, right? If you're feeling overwhelmed or you're just completely lost or whatever, right, come and talk to me and let's figure out a plan of getting back on track going forward. Yeah?
At some point, not necessarily today, but can you talk about how to organize something like that? Because that was one of the things I had.
Yeah, I'm going to talk about that in PA4 actually a little bit, and we can talk about other aspects of organization too. So there's no class on Monday, right? Monday's a holiday. But I plan to get these graded probably Saturday, Sunday, and get grades posted and some feedback. And then we can talk about specifics. Side note, I've been peeking in on this from time to time. So this got posted to Chegg almost 2 weeks ago, and still nobody has answered it on there. So I mean, it's a bit of a daunting project apparently because the experts at Chegg weren't able to answer it. So I'll look at what you did, and if it wasn't, you know, exactly what we wanted, we'll figure out what the details are. All right, so I posted an ODP, and since it's, you know, 10 o'clock in the morning when I posted it, so I'm giving you until Sunday morning, so it's a 2-day program, and it will help you with PA4. So let's look at that first. So ODP 211, you're building a small binary tree. And so for this ODP, we're working with a structure called a T node. Okay, that's a tree node. It has 3 pieces of information. It has the data field, which is an int, and then it has a field called left and right, which point to the left and right subtrees. Okay, and you're supposed to implement a function called small, which takes in 3 integers and builds a little tree. So if you call this function small, and you pass it a 5 and a 10 and a 15, what it should do is build a little tree with 5 at the root, 10 on the left, 15 on the right, and this thing returns a struct T node star. So if I call this R, then R would be the root of this little 3-node tree. And this is purely mechanical. There's no looping, there's no conditional statements, there's no function calls. This is just building nodes, declaring nodes by saying struct T node star, you know, name of the node, allocating space for it with malloc, and then setting the fields of the nodes so that you end up with this kind of looking tree. And so how do you do this? Define your structure, your struct T node. Make sure it's exactly like that. It's got to be data followed by left, followed by right. If you change the order, your code won't work. Okay, so make sure it's that order. And your small function can do something like this. Well, I'm going to build a tree where, you know, this is going to be A and B and C. I'm just going to call them that. And I'm going to say struct T node A equals malloc, size of struct T node. We've done this a billion times so far. So that's going to allocate a chunk of memory. It's going to make a variable named A, which is the address of this T node. And I'm going to do the same thing for B, and I'm going to do the same thing for C. So I've created 3 nodes. They're not in a tree, they're just nodes hanging out in space. Now I'm going to set their data values to be what I want, right? My goal is to take this first argument, put its value there, put the second one there, put the third one there. So A data equals 5. Well, don't set it equal to 5. Set it equal to the first argument, which is called root. Right, but I don't want to write the exact code. The second node, which is on the left, which I'm calling B, well, you want that data value to be equal to left, right? But if I was just hardwiring this, I'd do B data equals 10, and C data equals 15. Right, so these are args from, you know, that function call. So now I have 3 nodes hanging out in space, not connected to anything, but they have these data values in them. Now I want to build them into a tree. It's as simple as this. A arrow left equals B. A arrow right equals C. That builds these 2 links. Now A has 2 children. B doesn't have a child on the left, so I'll set B arrow left equal to null and B arrow right equal to null. And I can do the same thing for C, and when I'm all done, I want to return the root of this tree. Let's just return A. Okay, this is like calisthenics. It's like working at the bar in ballet class. It's fundamentals. It's almost like a warm-up exercise for PA4, right? Once you know how to do this, it may seem silly to be doing it, right? Once you know how to do, you know, down dog, it seems silly to keep doing it in yoga class because you already know how to do down dog. Well, you're doing it because, right, this is what you're going to build everything else on. And you want to be very comfortable, mentally very fluent with this idea of if I want A's left child to be B, I can just say A arrow left equals B, right? And there's a lot going on here. A arrow left equals B. Well, A is an address in memory, and I'm saying go to that address in memory, and now move down enough spots to get to the field called left, and that's an address in memory. And I want to change that address to the value of B, which is the address of the first piece of this struct T node that's being pointed to by B. Right? That's a lot of stuff going on. But if you can think of it as, oh yeah, I want A's left child to be B, I just do this, right? That's the fluency that we're after. And then when we start working with things like how do we add to a tree, how do we delete from a tree, how do we balance a tree, right? Then we won't get hung up on things like this. Okay, so this is a workout routine, and it's also, you know, basically something you're going to do in PA4 as you're developing it. All right, so make this function small, takes 3 integers, builds a 3-node tree, returns the root. Link it in with main to 11.0 and assess it. And the assessment's open till Sunday morning at 8. Does that make sense? All right, so I posted PA4 and I just revised this, so if you downloaded this before 11 o'clock, download it again, okay? Because there was a typo in there that's going to cause major galaxy-ending catastrophes if you follow it. So here's the revised version. Let me make sure this is the revised one. Yes, this is the revised one. Okay, so programming assignment 4, there's 6 pages, they're very dense, okay? Let me give you the one-sentence synopsis. PA4 is basically PA3 using a binary search tree instead of a hash. Okay, that's pretty much it. You're going to open the database file, you're going to pull in license plate records, you're going to build a binary search tree out of them, and then you're going to let the user type in a license plate, and you'll look it up in the binary search tree and tell them the name associated with it. There's a couple of commands you can use to look at the internal structures, just like dump and load in PA3. That's pretty much it. Okay, lots of details on how to do this, though. Okay, so sample program /temp/plate4, sample database, same as before. You can run that to sort of see what this program should do, but you can't do it until I actually write it, which won't happen until tomorrow. So sometime tomorrow, template4 will pop up, and I'll send an announcement when it's out there. And you can use that as a prototype. Okay, to run your program, you only have one way to run it. Name of the program, which must be plate, followed by the name of the database. Okay, no other options. There's no optional argument for hash size, because we don't have such a thing as a tree size. So it's just plate followed by the name of the database, which means your command line processing is a little simpler. argc's got to be equal to 2. And you take argv bracket 1, the second argument, you open it up as a database file, and you read it. If it's not run correctly, if it's not the program name with exactly one argument, just tell them it's an error and exit. User return 1. Okay, otherwise, if there's one argument, assume it's the name of a database, open it up with fopen, read in your records, assume that each line looks like this, 3 fields separated by a space. Okay, there's no restriction on what a plate looks like or what a name looks like, as long as it doesn't have spaces inside. So again, use scanf with 3% s's separated by spaces. That's the easiest way to pull these things in and break them up. Okay, license plate is the key. It's the piece of data that we're going to use when we search. It's the thing we're going to sort on when we build our tree. To make our tree a binary search tree, we need to have the things in the right order. The order is always determined by the license plate. The other fields, the name, just kind of come along for the ride. Right, they're pieces of the node, but it's really the license plate that we're using. Okay, once you've pulled in this whole database file, you've closed it up, now you just take commands from the user, and they type in something, and generally it's supposed to be a license plate search. So whatever they type in, search your tree for that. If you find it, print out the name. If you don't, print out an error saying plate not found. There's also 2 commands the user can type in. The first is *dump. And if they type that in, you're going to print out a bunch of information about the tree. That's the main command I'll use when I'm grading your program. Okay, because you're going to run the program, it's going to read in the database. The only way I know what's in there, other than searching for things, is going to be to use this dump command. So this is going to be really important. This is going to show me a bunch of information about your tree. Okay, the description is coming later on. The other command is delete. I can say *delete space followed by a license plate, and that should delete the plate from the database. Okay, remove it from the tree. All right, important detail here. There are a lot of different ways to delete things from a binary search tree. There's a lot of edge cases. We're going to talk about exactly one way to delete from a tree, and exactly one way to deal with the edge cases, and that's the way I want you to implement it. If you implement it with a different algorithm, chances are when I delete something, your tree is not going to look the way I expect it to, and it's going to cost points, because it's going to look like your delete function isn't working. And then you got to find me, and you got to show me your code, and you got to tell me why it's doing what it's doing, and I got to look at that and say, oh, okay, that's not as bad as I thought, and you might get some points back. Okay, it's a pain all around. So the safest way to avoid falling into a trouble area here is don't use any other sources for figuring out how to delete from a tree. Okay, use what we talk about in here. If you're not sure, ask. Right? ask me, shoot me an email, come to office hours, ask in class, ask me on Discord, whatever. Just because there's lots of, you know, helpful things out there on, oh, if you want to delete this, that's a special case, it's really easy to do, right? Well, that may be true, but if it's not the algorithm we're doing here, right, it's going to look like your delete doesn't work correctly. So try to stick to what we're talking about in here, and if you have questions on it, ask in here, right? Or if you think you know some fancy way to do this that's a whole lot easier, just come and ask me, you know, is it okay if I delete like this? And if it's effectively the same algorithm, that's fine. But if it's something different, I'll say, you know, don't do it that way. Okay, output details, when they type in a license plate and you find it printed out, same as you did in your hash function, your hash assignment. So first name, colon, last name, colon. And then ask them for another commander plate. Okay, if they say star dump, you want to print out a bunch of information. Please, please, please do it in this format, in this order, in this way, with nothing else in there, okay? Because again, this is how I'm going to grade. I'm going to take your program, going to load in the database, I'm going to dump, I'm going to delete some nodes, I'm going to dump, I'm going to do that 4 or 5 times, and I'm going to rerun your program with another database and do that, and I'm going to rerun it with a third and a fourth and probably a 5th database and do that. It means I'm going to be running your dump command 20 times or so, times 45 students, okay? That's a lot of staring at the output of the dump command. Don't make me search through a bunch of output that varies from this format, because I'm probably not going to see what you want me to see. I'm going to miss things and so on, yeah. Yeah, I wouldn't take off for that. That would give me a chuckle probably, but no. All right, so what does dump do? So first, print out the tree height, colon, height of the tree. Okay, don't just print 7. Eventually, I'll have someone who will do that. Hasn't happened yet. Print out the height of the tree. New line, balanced, colon, say either yes or no. Okay. Again, it's not a big deal, but if you say the tree is balanced or the tree is unbalanced, right? I can't just look at it and I'm expecting to see yes. I see a sentence and I have to read it. And I have to read it carefully because the tree is balanced and the tree is unbalanced look almost the same. And it's 2 characters out of all of it, right? So just stick to this. Balanced colon, yes. Balanced colon, no. Okay. And then empty line, please. And then LNR traversal colon, and then show me the results of doing this LNR traversal. Okay, we'll talk about traversals again. But basically, 1 line per node, plate, colon, angle brackets, plate, name, colon, last name, comma, first. Exact same format you used for dumping in PA3. Go through the whole tree, show me each node, 1 node per line. Empty line, NLR traversal colon, and then show me the same thing for the node left-right traversal. Empty line, LRN traversal colon, show me the same thing for the left-right node traversal. And then an empty line, and then go back to prompting the user. Does that make sense? And we'll talk about how to find the height and tell if it's balanced and how to traverse and all that sort of stuff. So that basically just shows the person running your program a bunch of information about your tree. Okay, the delete command, you say star delete. It should either say success if it found the node and deleted it, or it should say plate not found if it doesn't find it. That's really easy. Before you call the delete function, call the search function. See if the plate's found. If it's not, just say plate not found. This lets you guarantee that you're only calling delete when you know that the plate actually exists. That saves a bunch of edge cases. Okay, don't exit the program for any reason except when the user hits Control-D in the start of the line. So you try to delete a plate that's not found, don't exit the program. Okay, just keep going, asking the user for commands or plates until they hit Control-D. Once they do that, free your memory and then exit. Okay, very, very similar structure to PA3 as far as these details. All right, implementation. So your binary search tree is going to be a tree made out of nodes. Your nodes should look like this, 5 pieces to the node. 3 character fields for storing the plate, the first name and the last name. Those are char stars. They don't have any predefined length. So when you want to store something in there, you have to malloc based on the length of the thing you're storing plus 1. Exactly the same as PA tree. And then a pair of pointers left and right that point to the left and right child. So slightly different from ODP 211. 211 we're just doing integer nodes. Here they're a little more complex. And I'm setting up a struct node star that I call node with an uppercase N. You don't have to do this. But in the rest of this assignment, I'll refer to a node uppercase N. That's what I mean by an uppercase node. It's a struct node star. Okay, it's less typing. Almost everything we do with binary trees, we want a struct node star. Okay, the one exception is when we malloc space for a new node, we want a malloc size of struct node, not struct node star. Everything else, every temporary variable we declare, every return value is always a struct node star. So we can just call it an uppercase node if we want. There's no sentinel for trees, remember that. So an empty tree is just null. With list, we had a list init function. We could say, you know, my list equals list init, and that would create the sentinel node that points to null. For a tree, there's no such thing as a sentinel node, so an empty tree is just null. So here's what your initialization looks like in your main program. That should just be uppercase N. Node root equals null, right? Or struct node star root equals null. All right, required functions. So these are the functions you're going to call from your main program. You can make more functions if you like. Okay, but these are the ones that your main program will probably call. Make a function called height. Takes the root of a tree, returns an integer, which is the height. Empty tree should have a height of -1. Tree with just a root has a height of 0. And in general, it's the depth of the deepest node. All right, balanced takes the root of a tree and it returns an integer, which is a flag. If it's 1, it's telling me the tree is balanced. If it's 0, it's not. We have to talk about the balance algorithm still. But it's trivial. It's like 3 lines of code. Okay, add. So, bless you. So the add function, we pass it the root of the tree. We pass it the license plate, first name and last name we want to add. Okay, so plate first and last better be pointing to actual strings in memory somewhere. Okay, probably because we pulled them out of our database.txt file and we scanned them with scanf. Right, so they should point to things that have strings in them. And this will basically add a new node to the tree in the right place, and it returns the root of the tree. Usually the return root is going to be the same as the original root. One exception is if your tree starts off as empty. Because if I initialize my tree to be null, and now I pass null to my add function, when I come back from that function, my tree variable is still going to be null, right? Add can't change my local variables in main. So when I call add, I would say something like tree equals add parentheses tree comma plate first last. And the add function always returns the root of the tree after I've added something. Okay, we'll put some code together for that today. Search doesn't change anything, it just looks for a license plate. So pass it the root of the tree, the license plate you're looking for, and then pointers to strings where it will store the first and last name if it finds the plate. Okay, this is your list find function. So search for the plate in the tree. If it finds it, populate the first and last fields and return a 1 from search. If it doesn't find it, return a 0 from search. Don't change first or last. All right, delete is like add, but it's the opposite. We pass it a license plate and the root of the tree, and it should delete that node from the tree if it finds it. And it returns the root of the tree that has had that node deleted. And if it doesn't find it, just don't delete it. Don't print an error message or anything like that. But you can set it up so that you never call delete unless you know the node is in there by calling search first. All right, these are your three traversal functions. So traverse in order, pre-order, post-order. We'll talk about these more also, but basically LNR, NLR, LRN. Take the root of a tree, print out the contents, don't return anything. And then your free function takes the root of a tree, releases all the memory associated with that, and doesn't return anything. To release the memory from a tree, traverse the tree, start at the root and visit each node, right? And as you visit a node, release the memory that was allocated for the plate first name and last name, and then release the memory for the node itself. Yeah?
Since essentially lib already has a function called free, would we have to come up with a different name for it?
Oh, yeah. Come up with a different name. All right, that's another typo, because I also found one earlier. So I will fix that. We'll call it free tree. Yeah, don't call it free, because it'll get upset. Thanks. All right, does that make sense, what we're after here? All right, so I thought I would include a detailed set of suggestions for how to go about this, because it's a lot of stuff. And if you already have in mind how you think you're going to go about and do this, you can ignore my suggestions, okay? They're purely out there for if you're kind of stuck, I have no idea where to start or how to proceed, right? These may be helpful. So let me go through these, but you're not bound by these, okay? You can do it your own way if you like. So suggestions, step one, write some code to build yourself a tree, okay? This is kind of like what you're doing in ODP 211, but you're building it out of these struct nodes instead of these T nodes from 211. And you don't have to make a function to build a tree. You can just write a bunch of statements, right? Make a main program that just malloc space for a bunch of nodes, right? So A equals malloc, and B equals malloc, and C, D, E equal malloc. And set up some data fields. I don't know, set A to a 10, and B to a 5, and C to a 7, and D to a 3, and E to a 20. And put them into a tree. So A arrow left can be equal to C. A arrow right can be equal to E. And C arrow left can be equal to B, and B arrow right can be equal to D, and everything else is equal to null, right? And, you know, root equals A, and you've built yourself a little tree. Okay? It's a little bit of work, it's some typing, but if you do this, right, and maybe go into GDB and eyeball some of these things, start at the root and see what the left is, and see what the left is, and so on, right, it gives you something to work with. Okay? So like that. I'm using integers here, but make some data, right? Plate, first, last. And you can give these things fixed values, right? I can say something like root equals malloc size of struct node. I can set my plate to haha like that, right? That's a perfectly valid string. It's stable. It's not going to go away. And so when I access root arrow plate, it's going to be this string. Root arrow first name equals, you know, whatever you want. And I can do root arrow left equals, and, you know, if I'm calling this node C, I can set it equal to C. And I can set C plate and C first and C last and so on. So just cobble this thing together with just a bunch of statements. No looping, no conditionals, no functions or anything. Just a main program that just starts mallocing space, assigning values to fields. And when you're done, have a variable, which is a struct node star, that points to the root of that tree. And decide what kind of tree you want, right? Here's my standard tree. That's a nice fluffy tree. It's got 7 nodes. Well, do you want to type 7 times, you know, root equals malloc, root plate, root first, root last, root left, root right? That's 6 lines of typing times 7. Get better with VI. Use it as an opportunity to practice some VI. You can copy and paste. You can move around VI efficiently. And this is just, you know, linear code. It's not something you got to worry about indenting or looping or brackets or things like that. It's a good sort of practice area for playing with VI. And once you do this, you have a tree that you can use for testing most of the rest of PA4. Okay? And we don't have to worry about command line arguments and scanf and fgets and null and while this and curly bracket that and so on, right? Do these statements, you've got a tree. Now if I want to try printing it, I can just pass it to LNR and see if it prints. So second suggestion, code up LNR. Okay, LNR is 4 lines of code. If the root's null, return. Otherwise, LNR root arrow left, print root arrow plate, comma first, comma last, and then LNR root arrow right. And don't get bogged down with format for output and so on. This is purely for you, right? Code this up, make sure that LNR gives you the contents of your tree. And if you construct your tree to be a binary search tree where things on the left are smaller than the root, things on the right are bigger, LNR should show you the data you stored here in sorted order. Okay, for strings, remember to sort, use string compare. And if you call string compare on 2 strings, that's going to be less than 0 because cat comes before dog. Okay, if the first argument is bigger than the second one, it'll return something positive. If the 2 arguments are equal, it'll return 0. So string compare is how we sort these things. And yeah, lowercase cat comes after an uppercase dog. That's just life. Don't worry about it. Don't convert cases. Don't try to get fancy. Just use string compare. All right, so write your LNR code, make sure it's doing the right thing, and then go ahead and adjust the format to match the assignment. And then you don't have to think about it anymore. And it should print out all your license plate data in a nice format. Okay, so that's step 2. Step 3, while you're in here, go ahead and do NLR and LRN. They are exactly like left node right. You just change where you print the data. It's really just take that print line and move it above or below the 2 recursive calls. Okay, but do it now while you're thinking about it, and then you don't have to think about it anymore. Now you got a tree, you got 3 print functions. Step 4, work on your search. Okay, so code up your search. We talked about it the other day, but we'll go through the algorithm again next week. But basically, to search, you can see if the root's equal to the thing you're looking for. If it is, you're done. Otherwise, search the left subtree, search the right subtree, right? And ideally, before you do that, compare the thing you're looking for to the root. If it's smaller than the root, just search the left subtree. If it's bigger than the root, just search the right subtree. And test that. And again, you can test that very, very straightforward. Write some code. So have some space for first and last. Have an integer result, call search, pass it the root of the tree that you already built, a license plate, first and last. If it returns a 1, print out the values of first and last. If it returns a 0, say plate not found. And now make, 5 or 6 of these chunks of code to look for different license plates. Put in some that don't exist, put in the root, put in some leaves, put in some ones in the middle, and make sure that search is doing the right thing. So this is developing step by step, right? It's letting you concentrate on one function at a time and use the functions you've already built to help you develop the function that you're working on. If LNR works correctly, right, you should be able to do LNR on tree and see if it has a license plate in there, and then call your search function. And if it finds it, it should load in the first and last. Okay, this is another chance to get better with VI, because if you want to write 6 or 7 of these blocks of code, they're all exactly the same, except I want to change what that sum plate is to some other plate, right? That's very easy in VI if you're comfortable with some of the other features of VI. For example, you can use an uppercase Y to copy a set of lines. If I'm sitting on a particular line, I can say for uppercase Y, and it will copy those. It's called yanking to the yank buffer, but we call it copying to the clipboard in Windows. But that copies the code, and then I can move somewhere else and type a P, and it will paste those lines of code below where I'm sitting right now in the file. Okay. This is all when you're not in insert mode, by the way. If you're in insert and you say 4Y, it just adds 4Y to your file. Okay? If I'm trying to move through my file, I want to get to where it says yet another plate and change that with something else, right? I can get there with the arrow keys, but I can also use W and B to move a whole word at a time. And there's not a lot of words on there compared to characters, right? Yet another plate is one word. First is one word, last is one word. So W and B let you move very quickly across a line. If I hit enter to move down, it not only moves me down one line, but brings me back to the beginning of the line. And so now I can always hit W to move across. Whereas if I use an arrow key, I'm at the end of a string, then I got to go back to the beginning and so on. If I'm sitting right here, where it says yet another plate, and I want to change that word to something else, I can say CW. And CW is short for change word. It will let me type, and whatever I type will replace this entire word. I hit escape, and I've changed that to some other word. Right? And it could be shorter than, or longer than, or the same length as this. It doesn't matter. It'll just replace that word. So these are things to play with, right? When you have time, like if you're doing this weekend as opposed to, 5 in the morning, 2 weeks from today. It takes some time to play with this and get used to it, but I guarantee this will save you a ton of time the rest of your life. Right? If you're going to be coding, there's a good chance you're going to be working in VI or some other editor, right? And if you can be very efficient in that editor, you spend more of your brain power and your time working on your code as opposed to, playing a video game trying to find the double quote that you want to delete. All right, meanwhile, suggestion 5, work on your add function, okay? Again, just hardwire something. Just try adding a new plate with a call to add, save the result back in root, and then call LNR and see if it added it. And when you call LNR, it should print out your plate data in sorted order. Well, do that a few times. Add another plate, call LNR. Add a third plate, call LNR. Right? And it's still just a bunch of statements. There's no loops, no fgets, nothing like that. Okay, now for the trickier spot, start off by initializing root to null. Instead of this tree that you built in step 1, start off with root equals null and try adding stuff and printing it. And you should be able to build up a tree piece by piece like that. Once that works, make your loop to open up the database file. Again, you can hardwire this if you want. Don't worry about command line arguments. Just open this up with fopen, read the input with fgets, break it into plate first name, last name, pass it to your add function. And when you're done, close it. Now you got a big old tree with all of your license plate data in it. You can LNR it, you can search it, and make sure that that works. Now you can go ahead and do your height and balance functions, and those are small, but they don't really help you with the rest of this, so that's why I sort of put them later on here. They're small functions, they're recursive, it's a few lines of code. General comment, don't get hung up on this max function. When I write pseudocode, I use a function called max sometimes. There is no max function in C, okay? But you can go down a big rabbit hole Googling for the max function in C and finding all kinds of weird looking code that you can type in or things you can put in when you say GCC to include this max function and stuff you download and all that. Don't go down that path, okay? It's just pseudocode. Find the maximum of two numbers A and B, right? How do you do that? Use an if statement. If A is bigger than B, do the stuff you want when A is the maximum. Otherwise, do the stuff you want when B is the maximum or they're both equal. Or if you want to be fancier, make your own max function. Or define a macro, or whatever, okay? But you get to do this how you want, right? It's your world, basically. All right, and then you can probably go ahead and start working on your main program. So parse the command line argument. It's easier than it was in PA3 because there's only one possibility. Read in the database file. That's kind of the same as PA3, but you call your tree add instead of hash add. And then go into your loop where you fgets from the user, execute the command or do the search, and when they type in Control D, you exit your loop, free your memory, and you're done. And then step 10, go back and do your delete function. I would leave that for the end, because deleting is very tricky, has a lot of edge cases, and it can make other things break. If you delete incorrectly and then you try to do your LNR traversal, you might seg fault. It's not a problem with your LNR code. It's a problem with something that happened during delete. So you want to be pretty confident that your other functions work correctly, and you want to be as comfortable as possible with the whole sort of environment of working with these binary search trees, doing this arrow left, this arrow right, mallocing memory for plates, all that kind of stuff. You don't want to be doubting yourself on those, right? So if you do this at the end, you've got all this other experience to build on, and you can use that to help you figure out how delete is working. So delete a node, call your search function. If it still finds it in your tree, right, there's a problem with delete. Call your LNR. If it goes into an infinite loop, it's probably not a problem with LNR. It's probably a problem with the tree itself after you delete it. Okay, so those are suggestions, and modulate as you see fit. Timing-wise, you have a little less than 2 weeks to do this. Okay, 2 weeks minus about 4 hours. If you take the weekend off and you start this on Monday, you're down to 11 days. If you do daily work on your program from that point forward, and every day you finish one of these, you're leaving yourself 1 day of wiggle room to deal with, adding your comments and checking the final time through and pushing it to Git and all that kind of stuff. Some of these are going to take a lot more than 1 day. Some of them are going to take a lot less. So you got to pace yourself, okay? And I really suggest you start working on this today, particularly so that if questions come up, you can spend the weekend asking those questions, and be that much further ahead Monday or Tuesday. But we don't have class Monday, right? So so you really want to get going on this, and come up with a plan of attack. You can use this, you can modulate it or whatever. It's totally doable, okay? But it's not doable in one night in most cases. So you want to plan ahead. And then submission, plate PA4 on GitLab as usual. All right, let me talk about the add function really briefly. I'm just going to do this on a simplified node that just has an integer piece of data. Okay, so you'll need a more complex node. You'll have to use string compare instead of less than greater than. Okay, but just to give you an idea of the algorithm, how do we add a node to a tree? The usual approach would be if I want to add the number 8, I would start at the root. 8 is smaller than 10, I'm going to go to the left. 8 is bigger than 5, I'll go to the right. 8 is bigger than 7, I'll go to the right. Oh, there's nothing there. I'll back up, and on the right of that node, I'll put my new node 8. Okay? That's doable. You got to keep a pair of pointers for current and previous, so when you get down to the end, you know which way to go, and so on and so forth. We can do this recursively a lot more, not necessarily efficiently, but a lot easier in terms of code. Okay, so how do we add to a tree? Well, the first possibility is the tree is empty. If we're asked to add a node to an empty tree, what do? We just make a new root node, and that's our new tree. So if root is null, malloc space for a new root. Set the data field equal to whatever data you're trying to store, and return the root. So that's the edge case. Someone asks you to add to an empty tree, just make a root node containing the data and return that root node. Otherwise, we have some stuff in our tree already. We've been given this node over here. Well, to add our new number to this tree, we need to do exactly one of two things. We either need to add it to this subtree on the left or to this subtree on the right. How do we know which one to add it to? Well, if the thing we're adding is smaller than 10, add it to this subtree. Otherwise, add it to that subtree. So if data is less than root data, we want to add it to the left subtree. Well, how do we add a node containing data to the left subtree? Use your add function. So add to root arrow left num. And that add function is going to return the root of this left subtree. Well, that should be the left subtree of my original root. So what I'm going to do is I'm going to say root arrow left equals add root arrow left comma num. Otherwise, I'm going to call add on the right subtree, add num to that, and the root of the tree that it returns from that, I'm going to set my root's right subtree to be that. And when I'm done, I'm going to return root. And it's another 4-line function. Right? Base case, if there's no root, just make my default value. Right? Just make my root equal to that. Otherwise, right, 4 steps. If I want to insert to the left, insert on the left, change my left child to be that. Otherwise, insert on the right, change the right child to be that, and then return the root. So that's a working add function, right? That's pseudocode. But you can use that for adding license plates. Just do your comparison based on plates. And when you want to set the data equal to the data, right, you got a malloc space, you got a string copy of the plate first and last, and so on and so forth.
So when we're working with places, it's supposed to be in alphabetical order?
Whatever order string compare gives you, which will generally, it's ASCII code order. So if everything is uppercase, it'll be alphabetical. But if you have upper lowercase, it'll be out of order. All right. Seem doable? Cool. All right. I will see you next time. Have a good long weekend if I'm not seeing you in 2:15.